There is a year coming that most of us will live to see. It was calculated by human beings who lived 5,000 years ago. People who had no telescopes, no computers, no satellites. They had their eyes, their minds, and an unbroken commitment to watching the sky that lasted across dozens of generations. They worked in the flat river plains between the Tigris and the Euphrates, in the land that is now Iraq, and they kept records with a dedication that most modern institutions would struggle to match. The number they arrived at, the specific window of time their mathematics pointed to, is sitting in a glass case in London right now. Walk into room 55 of the British Museum on Great Russell Street, and you will find them. 2 clay tablets, each one roughly the size of a human hand, brownish gray, cracked at the edges, covered from corner to corner in tiny wedge-shaped marks, pressed into the surface with a cut reed. There is no dramatic spotlight on them. There is no crowd gathered around them the way crowds gather around the Rosetta Stone a few rooms away. There is a small label that reads Multablets Tablets, Mesopotamia, approximately 700 BCE. Most visitors give them 4 seconds and walk on. Those 4 seconds are the cost of walking past one of the most precise astronomical calculations ever produced by human hands. These tablets were pulled from the ground at Nippur, a city that once stood in what is now the Diq province of southern Iraq, roughly 200 kilometers south of Baghdad. The excavation began in the 1880s, when teams working under the Babylonian expedition of the University of Pennsylvania started moving through the ancient mounds at that site. What they found was not a palace or a treasury, it was knowledge. Thousands upon thousands of cuneiform tablets, layer upon layer of recorded information, pressed into clay and left to survive whatever came next. Nippur was never a military capital. It was a city built almost entirely around the life of the mind. Temples, scribal schools, observational platforms, and record archives concentrated in one place across thousands of years of continuous occupation. If you wanted to understand the sky in the ancient world, Nippur was where the serious work happened. The Mulapin tablets found there carry a date of around 700 BCE, but the astronomical observations written on them are believed to be considerably older. Scholars who have studied the tablets closely estimate that the data they contain was already several centuries old when these particular copies were pressed into fresh clay, going back to at least 1200 BCE and possibly much further. The people who made these copies were not creating new knowledge. They were maintaining a chain, deliberately copying what their predecessors had recorded, preserving it in the most durable medium available to them, and passing it forward to whoever came next. That act of copying was itself a statement. This information matters enough to keep. Someone ahead of us is going to need it. On the surface, the tablets read as a combined star catalog and astronomical manual. They track the rising and setting positions of major stars across the full year. They follow the moon through its monthly cycle. They record the movement of 5 visible planets. They describe the path of the sun through every season. Any serious student of ancient astronomy would find these tablets extraordinary for those contents alone. But underneath all of that, running beneath the day-to-day sky, records the way a deep river runs beneath a visible current. There is something much larger, a calculation that is not concerned with what the sky does over a year or a decade, but with what it does over thousands of years. A calculation about the largest cycle the Sumerian astronomers had detected in all their generations of observation. That deeper calculation is what this documentary is built around. To understand why it matters, and why the number it produces points directly at the decades most of us are living through right now, we first have to understand the people who made it. Because the natural question any careful person asks, when told that an ancient civilization calculated a specific date, 5,000 years in their future, is a simple one. Why should we trust them? What evidence do we have that these people were doing real science, rather than constructing elaborate mythology, dressed in astronomical language? The evidence is extensive, and it is independently verifiable. The Sumerians calculated the synodic period of Venus, the time Venus takes to return to the same position relative to Earth and the Sun, at 584 days. Modern astronomy using satellite measurement puts the Venus synodic period at 583.92 days. That is a margin of error of less than 1/10 of 1%, produced through naked eye observation alone, sustained across multiple generations of sky watching. That single data point tells you something important about the quality of attention these people brought to their work. Jupiter's orbital period was recorded in their system at 12 years. The modern figure is 11.86 years. The Enuma Anu Enlil, a real series of 70 cuneiform tablets that is among the most studied astronomical records from the ancient world, contains over 7,000 individual celestial observations. Each one is a specific event tied to a specific observable sky condition. This is the work of a scientific institution, not a group of storytellers. Assyriologist Hermann Hunger and astronomer David Pingree spent years analyzing these records and published their findings in a study called Astral Sciences in Mesopotamia in 1999. Their conclusion was that a substantial portion of these observations are astronomically accurate and cross-verifiable against modern calculations of what the sky looked like over ancient Mesopotamia at the time those observations were made. These were real scientists working with real data across real generations of sustained observation. The question is, what they found when all that data was examined together. What does the sky reveal when you have not just your own lifetime of watching, but the accumulated records of hundreds of years behind you? What becomes visible at that scale that is completely invisible at any shorter scale? The answer is a motion so vast and so slow that most of human history has passed without the majority of civilizations ever detecting it. A turning of the entire sky itself, so gradual that it takes nearly 26,000 years to complete one full rotation. The Sumerians saw it. They measured it. And from that measurement, they produced a calculation that crosses 5,000 years and lands almost precisely on the moment we are living through right now. In the southern desert of Iraq, not far from where the Euphrates once ran before the river shifted its course over centuries, there are mounds rising out of the flat land that from a distance look like natural hills. They are not natural. They are the compressed remains of Tel al-Mukayyar, the ancient city of Ur, one of the largest and most sophisticated urban centers the ancient world produced. At its peak, around 2000 BCE, Ur held an estimated population of 60,000 people, making it one of the most densely populated places on Earth at that time. It had paved streets, a drainage system, a harbor connected to a network of canals, and at its center, a ziggurat, a massive stepped tower built from millions of fired bricks that rose high enough above the flat plain to be seen from a considerable distance in every direction. That ziggurat was not purely a religious monument. Its upper levels functioned as an elevated observation platform. Above the dust and the heat shimmer of the desert floor, the sky was clearer and the horizon more visible. Trained observers stationed there night after night, season after season, year after year, built up a record of the sky that accumulated detail and precision, the way a sediment layer builds up on a riverbed, slowly, continuously, in a way that only becomes fully visible over a very long time. The people doing this work were professionals in the most serious sense of the word. Scribal education in ancient Sumer and Babylon began in childhood and lasted years. Students attending the Ejaba, the scribal school, memorized mathematical tables, learned the Sumerian and Akkadian names and positions of hundreds of stars and constellations, studied the observed patterns of planetary motion, and began their own night observation sessions as part of formal training before they were considered qualified to contribute to the institutional record. This was a career with standards, examinations, and a body of accumulated knowledge that had to be mastered before a person was trusted to add to it. The University of Chicago Oriental Institute, which has spent over a century translating and analyzing cuneiform texts from collections around the world, holds in its published records a detailed picture of how this scribal astronomical tradition functioned as an institution. It was not a loose collection of individual observers each doing their own thing. It was an organized system in which observations were recorded in standard formats, checked against previous records, and stored in archives that were maintained across political changes and dynastic transitions. When one ruling power replaced another in ancient Mesopotamia, the scribal institutions often continued operating. The knowledge was considered too valuable to destroy. That institutional continuity is what made the detection of the Great Slow Cycle possible at all. No individual observer, working within a single human lifetime, could have detected a motion that takes nearly 26,000 years to complete. The motion is simply too slow. In any given decade, the change in the sky's position is so small that it falls below the threshold of what naked eye observation can reliably distinguish. But across a century it becomes detectable. Across several centuries it becomes measurable. Across 1,000 years of carefully maintained records it becomes a verified phenomenon with a measurable rate. The Sumerians had that kind of record, and they used it with mathematical tools that the modern world has consistently underestimated. Their number system was built on a base of 60 rather than the base 10 system used by most of the modern world. 60 is a remarkable number mathematically because it can be divided evenly by 12 different whole numbers, specifically 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60 itself. 10, by contrast, can only be divided evenly by 4 whole numbers. This gave the Sumerian mathematical system a natural flexibility for working with fractions and large numbers that made it genuinely superior for astronomical calculation. It is not a coincidence that we still divide hours into 60 minutes, and minutes into 60 seconds, and circles into 360 degrees. Those conventions were inherited directly from Sumerian mathematics and have survived for 5,000 years because they serve astronomical and geometric calculation better than the alternatives. Using this mathematical foundation, Sumerian astronomers were doing things that European mathematics did not formally develop until the medieval period. The cuneiform digital library initiative at UCLA has been systematically digitizing tablets from collections around the world, and the mathematical tablets in their database demonstrate operations equivalent to algebra, geometric series, and what we would now call trigonometric calculation, all present in ancient Mesopotamia, thousands of years before the civilizations usually credited with developing these methods. The most dramatic demonstration of their predictive mathematical capability is the Saros cycle. The Saros is an 18-year and 11-day period after which lunar eclipses repeat in a predictable pattern. The Babylonians identified this cycle and used it to predict eclipses before they happened. British Museum tablets in the Saros series record predicted eclipse dates that modern astronomy can verify were accurate. These people were not just cataloging what had already happened. They were projecting forward in time, using mathematical patterns extracted from their observation record. That capability, verified and confirmed by modern researchers, is the same capability that produced the long-range calculation this documentary is about. When a body of people with this track record, this institutional continuity, this mathematical sophistication, and this demonstrated ability to project forward in time, produces a calculation pointing to a specific window in the future, that calculation deserves to be examined carefully. The number they produced, and the astronomical mechanism behind it, is what the next part of this documentary explains. Take a spinning top and set it going on a flat surface. While it is spinning fast, it stands upright, and the tip traces a tight circle. As it gradually slows, something changes. The top does not fall over immediately. Instead, the upper part begins to lean and sweep slowly around in a wide circle, while the tip stays on the ground. That slow sweeping motion of the tilted axis is called precession. Every child who has played with a top has seen it happen. What almost no one realizes is that the Earth does exactly the same thing on a timescale so vast that the entire span of recorded human history covers only a fraction of one complete sweep. The Earth spins on its axis once every 24 hours. That axis is not perfectly upright. It tilts at an angle of about 23.5 degrees relative to the plane of its orbit around the Sun, and like the slowing top, that tilted axis sweeps slowly around in a great circle. One complete sweep takes approximately 25,772 years. This motion is called the precession of the equinoxes. It is a real, measurable, ongoing astronomical phenomenon. It is not mythology. It is not interpretation. It is observable with modern instruments, and its rate has been measured with precision using satellite technology. The visible effect of this precession for an observer on the ground is subtle, but consistent. The point in the sky that the Earth's axis points toward shifts slowly over time. More importantly for ancient sky watchers, the position of the constellation sitting directly behind the Sun on the spring equinox The day in late March, when daylight and darkness are of equal length, changes over the centuries. The equinox sunrise moves backward through the zodiac at a steady rate, spending roughly 2,160 years in each constellation before moving into the previous one. In our current era, the equinox sunrise is in the constellation Pisces, moving toward Aquarius. Before Pisces, it was in Aries. Before Aries, it was in Taurus. Ancient records from multiple cultures reflect awareness of these transitions. The age of Taurus corresponds to a period when bull symbolism dominated religious and cultural iconography across multiple civilizations simultaneously. The transition to Aries brought ram symbolism to prominence in cultures from Egypt to Persia. These shifts were not coincidental. They reflected a real change in the astronomical backdrop that sky-watching cultures were oriented toward. The city of Babylon, standing roughly 85 kilometers south of modern Baghdad in the Babel province of Iraq, was the intellectual capital where the Babylonian inheritors of the Sumerian tradition refined and extended this understanding into the most complete astronomical framework the ancient world produced. The Pergamon Museum in Berlin today houses the reconstructed Ishtar Gate from Babylon, built by Nebuchadnezzar II around 575 BCE. The gate is decorated with astronomical and zodiacal symbols and was the entrance to a city that maintained active astronomical institutions, producing continuous sky records. The scale and organization of that civilization is difficult to fully appreciate from the outside, but the physical remains give some sense of it. This was a serious urban intellectual culture, with centuries of sustained institutional investment in understanding the sky. The academic work that most thoroughly documented ancient awareness of precession is Hamlet's Mill, written by Giorgio de Santillana, a historian of science at MIT, and Hertha von Dekend, a historian of science at Frankfurt University, and published in 1969 by Gambit Press in Boston. Their research traced awareness of precessional motion through the mythological and astronomical records of dozens of ancient cultures, and identified Mesopotamia as one of the earliest and most mathematically precise sources of this knowledge. The book is a standard academic reference and has been engaged with seriously by historians of science for over 5 decades. What the Sumerians built from their detection of this motion was a framework for understanding time on the largest scale available to human observation. They called the full 25,920-year cycle, using their own calculated figure, the Great Year. They divided it into 12 equal ages, each lasting approximately 2,160 years, corresponding to the 12 constellations of the zodiac, through which the equinox sunrise moves during one complete precessional cycle. They tracked the sequence of ages, identified which age they were currently in, calculated the rate of movement through that age, and projected forward to when the current age would end and the next one would begin. This framework was the clock they built. A clock that no single human lifetime was long enough to read, but that generations of accumulated records made readable to those with the patience and the institutional structure to maintain the observation. The Sumerians had both. Their clock was running, and the number it produced when they applied it forward in time from their documented observational starting point is the specific calculation this documentary has been building toward. The mathematical method they used to arrive at that number is more precise and more rigorous than most people assume when they first encounter it. Walking through that method carefully, using the actual numbers the Sumerians recorded, is how we arrive at a date that lands inside the lifetimes of the people watching this documentary right now. The Sumerian number system gave their astronomers a tool for precision that is easy to underestimate if you have never thought carefully about what different number bases actually make possible. When we count in tens, we are using a system that divides naturally into halves and fifths, and not much else. 10 divided by 3 gives you a repeating decimal that never resolves cleanly. 10 divided by 4 gives you 2.5, but 10 divided by 6 gives you another messy repeating number. For everyday commerce and basic accounting, base 10 is perfectly adequate. For astronomical calculation involving the division of large cycles into precise fractions, it is genuinely clumsy. 60 divides cleanly into 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Any calculation requiring these divisions, which astronomical calculation constantly does, produces clean whole number results rather than the approximations and remainders that base 10 forces on you. When the Sumerian astronomers needed to divide a large cycle into equal parts, or calculate how far through a cycle a particular position represented, their number system handled the arithmetic smoothly in a way that would have required significantly more rounding and approximation in base 10. The Cuneiform Digital Library Initiative at UCLA maintains the most comprehensive digital archive of cuneiform tablets in the world. Mathematical tablets in that archive demonstrate that Babylonian mathematicians, working in the tradition inherited from the Sumerians, were performing operations equivalent to quadratic equations, geometric series calculations, and early forms of what we would now recognize as trigonometric reasoning. These capabilities were present in ancient Mesopotamia, roughly 1,500 years before Greek mathematics, which is usually credited as the origin of these methods in Western historical accounts. With these mathematical tools, the Sumerian astronomers extracted from their long observational record a specific rate of precessional movement. Their figure was 1 degree of movement every 72 years. To understand what this means practically, a full circle contains 360 degrees. The zodiac belt through which the equinox sunrise moves during a precessional cycle is a full circle, at a rate of 1 degree per 72 years. Completing the full 360-degree circle takes 360 multiplied by 72, which equals 25,920 years. That was their figure for the length of one complete great year cycle. Modern astronomy, using satellite measurement and laser ranging and computational tools that would have been incomprehensible to the ancient world, puts the precessional cycle at 25,772 years. The Sumerian figure of 25,920 differs from the modern figure by 148 years, across a 25,000-year cycle. That is a margin of error of 0.57%. Their rate of 1 degree per 72 years compares to the modern measurement of 1 degree per 71.6 years, a difference of less than half a year per degree across the entire cycle. These numbers establish something important. This was not an approximation or a rough estimate. This was a careful measurement, extracted from a long record of careful observation, and it is accurate to a standard that a professional astronomer working today would find difficult to dismiss. The starting point for their forward projection was their own observational position in the precessional cycle. The earliest Sumerian astronomical records, going back toward 4000 BCE, show the spring equinox sunrise positioned in a particular part of the zodiac. Working forward from that documented starting point at their measured rate of 1 degree per 72 years, the Babylonian successors to this tradition could calculate with considerable precision when the equinox sunrise would cross from Aries into Pisces, and from Pisces into Aquarius. The demonstrated predictive capability that confirms they were applying this mathematics correctly, rather than simply cataloging backward-looking records, is the Saros cycle, an 18-year and 11-day period after which the pattern of lunar eclipses repeats. The Babylonians identified this cycle, calculated its period, and used it to predict specific eclipses before they happened. British Museum tablets in the Saros series include predicted eclipse dates that modern astronomy can verify were accurate. The methodology is identical to the Great Year projection. Identify a cycle, measure its period precisely, apply that period forward from a known position to predict where the system will be at a future point in time. The Great Year calculation, using their own numbers, applied forward from their own documented observational starting point, produces a transition window from the age of Pisces to the age of Aquarius that falls within the 21st century. The central point of that transition, the moment when the equinox sunrise has moved fully across the boundary between the two constellations in their framework, sits between 2060 and 2080 CE by the most widely cited scholarly calculations using the Sumerian method. That number did not stay in Mesopotamia. It did not die with the cities that produced it. It traveled across time and geography through a chain of preservation that is itself one of the more remarkable stories in the history of human knowledge. And understanding that chain is what allows us to trust that the number we have received today is the same number the Sumerians actually produced. In 612 BCE, a combined army of Babylonians and Medes surrounded the city of Nineveh, which stood on the eastern bank of the Tigris River, near what is now the city of Mosul in northern Iraq. After a siege of several months, the walls were breached, and one of the most powerful cities the ancient world had produced was destroyed. The palaces burned. The administrative buildings collapsed. The city that had been the capital of the Neo-Assyrian Empire for generations ceased to exist as a functioning urban center almost overnight. Beneath the rubble of one of those palaces, buried under collapsed ceilings and burned wooden beams, lay over 30,000 clay tablet fragments. They had been placed there deliberately by Ashurbanipal, who ruled the Neo-Assyrian Empire from 668 to 627 BCE, and who had spent decades building the most comprehensive library the ancient world had yet seen. Unlike the paper and papyrus records that burned in their thousands in other ancient libraries, the clay tablets at Nineveh survived the destruction of the city. The fire that brought the palace down actually completed the firing process on tablets that had only been air-dried, making them harder and more permanent than they had been before. Ashurbanipal's obsessive collection of knowledge survived the destruction of the empire that housed it. Archaeologists working under Austin Henry Layard and later Hormuzd Rassam began excavating the Nineveh Palace site for the British Museum in 1849. The tablets they pulled from the ground over subsequent years included the full range of Babylonian and Sumerian intellectual production that Ashurbanipal had gathered: mathematical records, medical texts, literary works including the Epic of Gilgamesh, and the astronomical records, the Mullah-Pin tablets, the Enuma Anu Enlil series, the Saros cycle tablets, all carrying the full processional framework that had been built up across centuries of Sumerian and Babylonian skywatching. But the story of how this knowledge survived does not begin with Ashurbanipal, and it does not end with Nineveh. Ashurbanipal built his library partly from copies made across his empire, which means the knowledge he was collecting had already been copied and distributed before his reign. When the Neo-Assyrian Empire fell, the knowledge had already traveled westward through scribal networks that extended beyond its political borders. It reached Egypt, where the Library of Alexandria, at its peak in the 3rd and 2nd centuries BCE, became the intellectual clearinghouse for knowledge from across the ancient world. Babylonian astronomical texts arrived there and were studied by Greek scholars who began translating and engaging with them seriously. The most direct documented transmission of the Sumerian processional framework to the Greek world came through a Babylonian priest named Berossus. Around 290 BCE, Berossus established a school on the Greek island of Kos and wrote a work in Greek called Babyloniaka, a 3-volume account of Babylonian history, astronomy, and cosmology, intended to make Mesopotamian knowledge accessible to a Greek audience. Berossus is confirmed as a historical figure by multiple ancient sources. Josephus, the 1st-century Jewish historian, references him. Vitruvius, the Roman architect and writer, mentions him in connection with the sundial. His work transmitted the concept of the Great Year, the precessional cycle, and its division into ages, directly into Greek intellectual culture. Greek philosophers absorbed and adapted the concept. Plato referenced the Great Year in his dialogue Timaeus. Aristotle engaged with long astronomical cycles in his work on cosmology. The Stoic philosophers made the concept of a great cosmic cycle central to their understanding of time. Each of these engagements changed the vocabulary and the philosophical framing, while preserving the astronomical core that the Sumerians had originally calculated. From Greek philosophy, the concept passed into Latin intellectual culture through writers like Cicero and Virgil. From there it moved through the medieval Islamic scholarly tradition, which preserved and extended a great deal of ancient astronomical knowledge during the centuries when it was less actively studied in Europe. From there it returned to European intellectual life during the Renaissance, when ancient texts were being recovered and retranslated. At each stage of this journey, the specific astronomical calculation was carried inside philosophical and cosmological frameworks that changed in character depending on the cultural context. But the mathematics inside those frameworks, the precessional rate, the 2,160-year age length, the sequence of ages moving through the zodiac, remained consistent because those were numbers that anyone with sufficient observational capability could independently verify. The mathematics was the anchor that kept the calculations stable across all the translations and cultural adaptations it passed through. By the time modern astronomers and historians of science began examining the ancient records with contemporary tools, the calculation was still there, intact, verifiable, and pointing at a specific window of time that, when the full chain of transmission is understood, carries the weight of everything that has been described in this documentary so far. Stand on the hill at the Greenwich Royal Observatory in London on a clear night and look south across the city. The sky above the Thames Basin is never fully dark because of the city's light, but the brightest stars are visible, and the general orientation of the zodiac belt across the sky is clear enough to give a sense of the geometry involved. This is one of the institutions that formalized the astronomical measurement conventions the modern world uses. The Greenwich Meridian, the prime meridian of longitude, runs through this building. The time kept here, Greenwich Mean Time, was for a century the global standard. Standing on this hill gives a sense of what serious institutional astronomy looks like, and has looked like for centuries. It also gives a sense of the continuity of the enterprise. The Sumerian astronomers in Nippur and the astronomers at Greenwich were doing the same thing at the most fundamental level. They were watching the sky carefully, measuring what they saw as precisely as their tools allowed, recording those measurements, and building frameworks to understand what the measurements meant over long periods of time. The tools were different. The precision improved. The underlying activity was the same. Now for the specific number that this documentary has been building toward. The age of Pisces, in the Sumerian and Babylonian framework, began when the spring equinox sunrise position crossed from the constellation Aries into the constellation Pisces. The historical and astronomical records place this transition at approximately 26 BCE. This is not a single scholar's estimate. Multiple independent researchers working with the ancient records and with modern astronomical calculation of where the equinox was positioned at various historical dates have arrived at dates in this general range. The variation between different scholarly estimates is a matter of a few decades in either direction, which in the context of a 2,160-year age is a very small margin. Take 26 BCE as the starting point and apply the Sumerian figure of 2,160 years per age. Adding 2,160 to the starting point gives a transition date of approximately 234 CE. That is the far end of the window by the straightforward arithmetic. But the transition is not a single moment. Constellation boundaries are not sharp lines in the sky. They are fuzzy zones where the equinox sunrise is leaving one constellation's influence and entering another's. The transition window is a period rather than a precise date, and the width of that window depends on how the constellation boundaries are defined. Astronomer Jean Meus, whose book Astronomical Algorithms, published in 1991, is a standard professional reference for precision astronomical calculation, addressed this question using the formal constellation boundaries established by the International Astronomical Union in 1930. The IAU boundaries were defined by the Belgian astronomer Eugène Delporte, using a system of right ascension and declination coordinates. By those strict modern technical boundaries, the equinox sunrise does not fully clear the constellation Pisces until around 2597 CE. However, the Sumerian method did not use the IAU boundaries. Their age divisions were based on equal 30-degree segments of the zodiac, measured from a fixed reference point in their own observational framework. Using their own measurement system rather than the modern technical boundaries pushes the transition window significantly earlier. The most widely cited scholarly calculations applying the Sumerian equal division method to the known precessional rate place the transition window opening in the early 21st century and the central transition point, the midpoint of the boundary crossing, between 2060 and 2080 CE. This is the year the title of this documentary refers to. This is the return date the Sumerian astronomers calculated. The return of an astronomical condition, the crossing of the equinox sunrise from Pisces into Aquarius, that they identified as marking the beginning of a new 2,160-year age in their Great Year framework. Most people watching this documentary will be alive in 2060. A person who is 35 today will be 70 in 2060. A person who is 20 today will be 55. A child born this year will be in their mid-30s. The window is not distant. It is within the span of living memory for the majority of the global population as it exists right now. The Sumerians who calculated this transition recorded something else alongside the mathematics. They left observations about what previous transitions had looked like. drawn from the long historical memory their institutional record gave them access to. Those observations, pressed into clay thousands of years ago, describe conditions that carry uncomfortable familiarity when placed next to a description of the world in the early 21st century. The Louvre Museum in Paris holds one of the most significant collections of ancient Mesopotamian material outside of Iraq. In the Richelieu wing on the ground floor, running through a series of connected rooms, there are case after case of Sumerian and Babylonian objects. Cylinder seals the size of a finger, pressed into clay to leave their images behind. Votive statues placed in temples as permanent stand-ins for worshippers who could not be present in person. Boundary stones marking land ownership with astronomical symbols carved into their surfaces, and among them, in translation, the contents of texts that go beyond astronomical calculation and into something that reads very differently 5,000 years after it was written. The Enuma Elish is a Babylonian text recorded on 7 clay tablets. In its written form, it dates to the 12th century BCE, though the underlying material is considerably older. It is usually described as a creation myth, and in one sense it is. But embedded within its narrative is a framework for understanding cosmic cycles and the conditions associated with different phases of those cycles. The Atrahasis is an Akkadian epic that predates the Enuma Elish and deals with creation, human civilization, and a great flood that reshapes the world. Both texts have been translated and published by the British Museum Press. The standard scholarly translation and analysis is the work of W.G. Lambert, whose research on Babylonian literary texts was published by Oxford in 1960 and remains a foundational academic reference in the field. The ancient city of Lagash, excavated near the modern town of Al-Shatra in the Diyakar province of southern Iraq, produced some of the oldest surviving Sumerian administrative and religious texts. Lagash was a major center, and its records extend back to the early Sumerian period. Among its texts are descriptions of what the Sumerians understood to be characteristic conditions of transitional periods between ages in their Great Year framework. Those descriptions are worth examining carefully and precisely, without embellishment, and without the kind of dramatic framing that tends to follow ancient texts when they enter popular culture. The Sumerian records describe transition periods as times when established structures of organization come under pressure that they were not designed to handle. The systems that had maintained stability during the previous age, political, economic, social, begin encountering conditions that exceed their design parameters. This is not described as catastrophe. It is described as a structural mismatch between existing institutions and new conditions, a mismatch that forces reorganization. The records describe transition periods as times of rapid change in the natural world, agricultural patterns that had been reliable for generations becoming less predictable, environmental conditions shifting in ways that require communities to adapt their practices rather than continuing what had previously worked. The land and climate behaving differently than the long-term record suggested they should. The records describe a breakdown in the boundaries between knowledge that was previously held by specialist groups and the broader population. Ideas and information that had been the province of scribal or priestly institutions, spreading outward and becoming accessible to people who had previously had no contact with them. This democratization of knowledge is described in the transition texts as both disorienting and generative simultaneously. The records describe the questioning of belief systems and social hierarchies that had been taken for granted during the previous age. Not the replacement of one set of beliefs by another in a clean transition, but a period of genuine confusion during which multiple competing frameworks exist simultaneously, and the resolution between them is not yet clear. And the records describe what comes after this period of disruption: a new foundation, a reorganization that is not a restoration of the previous arrangement, but a genuinely new structure, built from the conditions the transition period created. The Great Year does not stop turning when one age ends. It continues into the next one. The disruption is a passage, not a destination. It is essential to be clear about what these texts are doing. The Sumerians were not claiming prophetic knowledge of specific future events. They were recording patterns observed across their long institutional memory of previous cycle transitions, and applying those observed patterns as general expectations for the character of future transitions. They were doing what any careful observer of repeating cycles does. They were noting what had been true before, and projecting that it would be true again, in roughly similar form. Whether those observations constitute reliable pattern recognition across civilizational cycles, or represent the natural human tendency to find familiar shapes in historical data, is a question each person watching this documentary has to answer for themselves. What is harder to dismiss is what happens when those ancient descriptions are placed next to the findings of modern scientific institutions that approach the same time window from completely different directions. The NASA Jet Propulsion Laboratory sits in the foothills of the San Gabriel Mountains in Pasadena, California, and it is one of the most technically sophisticated research facilities on Earth. The teams working there calculate the positions of planets, moons, asteroids, and active spacecraft to accuracies measured in meters across distances of hundreds of millions of kilometers. The precision required for this work is extraordinary, and it depends on having a long baseline of accurate astronomical observations to anchor calculations against verified historical events. One of the sources that JPL scientists use for this long baseline is the Babylonian eclipse record. The Saros series tablets, which record predicted and observed eclipse dates across centuries of Babylonian astronomical work, are accurate enough to serve as calibration data for 21st century spacecraft navigation calculations. A modern space agency is operationally using ancient Mesopotamian astronomical records because those records are reliable. That is the context in which the following convergence should be understood. The Intergovernmental Panel on Climate Change published its sixth assessment report in 2021. This document represents the consolidated scientific findings of thousands of researchers across dozens of countries working over multiple years, examining every aspect of Earth's climate system using the most comprehensive data set ever assembled on the subject. Its conclusions about the mid-21st century are stated with high scientific confidence. The period between 2040 and 2080 represents the most critical inflection point in Earth's climate trajectory in the entire span of recorded human history. The emissions, land use, and energy decisions made within that window will determine which of several fundamentally different climate conditions persists for centuries afterward. The IPCC does not use the language of ages or precessional cycles. It uses the language of parts per million and radiative forcing and tipping point thresholds. But the window of time it identifies as the decisive period is the same window the Sumerian precessional calculation points to. The Santa Fe Institute in New Mexico is dedicated to the mathematical study of complex systems, the kind of large interconnected systems that include economies, ecosystems, and civilizations. Researchers there have built mathematical models of how large, complex social structures behave over long time periods. Their modeling identifies recurring patterns in how civilizations develop and how they respond to the accumulation of stress across multiple interconnected systems simultaneously. The output of those models, applied to the current global situation, points toward the mid-21st century as a period when multiple complex systems, financial, ecological, political, technological, are likely to be under simultaneous pressure in a way that has not occurred in the historical record. Ray Kurzweil, whose career spans engineering, artificial intelligence research, and the study of technological change, published The Singularity is Near in 2005 through Viking Press. His analysis of the exponential growth curves in computing power, biological knowledge, and materials science led him to project a convergence point in the 2040s through 2060s, when the rate of technological change becomes so rapid and the implications so fundamental that the world after that point functions according to different rules than the world before it. He borrowed the term singularity from physics to describe a transition point from which previous conditions cannot be extrapolated forward. His specific projected window sits squarely inside the same mid-century period. None of these researchers consulted the Mulla-Pin tablets. The climate scientists modeling greenhouse gas concentrations had no interest in Sumerian cosmology. The complexity theorists at Santa Fe were building mathematical models, not reading ancient texts. Kurzweil was tracking transistor densities and genome sequencing costs. They arrived at the same window through methodologies that share no common origin. What this convergence suggests, and this documentary presents it as a suggestion rather than a conclusion, is that the mid-21st century may be a window of genuine systemic significance that is detectable through multiple independent approaches. The Sumerians detected it through the long observational record of a slow astronomical cycle. Modern science is detecting it through climate data, complexity modeling, and technological trajectory analysis. The methods are separated by 5,000 years of human development. The window they point to is the same. There is a version of this documentary that could be made, in which ancient astronomical records are treated as colorful historical background, and the real conversation happens among contemporary researchers who have moved beyond such things. That documentary would misrepresent the actual state of the field. The engagement between serious working scientists and the Babylonian astronomical record is not a fringe activity. It is not confined to enthusiasts or alternative historians. It is happening in peer-reviewed journals, in major research universities, and in institutions that carry significant scientific credibility. Giulio Magli holds a position in mathematical physics and archaeoastronomy at the Polytechnic University of Milan, one of Italy's leading technical universities. His published research, which appears in the Journal for the History of Astronomy and other peer-reviewed publications, addresses the awareness and mathematical treatment of precessional motion in ancient cultures, including Mesopotamia. His work treats the Sumerian and Babylonian astronomical tradition as a subject of serious scientific historical inquiry, examining what these cultures actually understood about the sky, and how that understanding was encoded in their records and their built environments. His approach is methodologically rigorous, and his conclusions, which acknowledge genuine sophistication in ancient astronomical knowledge, have been engaged with seriously by other researchers in the field. The Max Planck Institute for the History of Science in Berlin is one of the most prestigious research institutions in the world for the study of how scientific knowledge developed across human cultures and historical periods. The institute has a dedicated research program focused specifically on Babylonian mathematical astronomy. The scholars working in this program have produced detailed analyses demonstrating that Babylonian planetary models, the mathematical systems Babylonian astronomers used to calculate and predict planetary positions, anticipated mathematical techniques that European astronomy did not develop until the late medieval period. Their work has substantially revised the standard historical account of where sophisticated mathematical astronomy originated and when. At NASA's Jet Propulsion Laboratory, the use of Babylonian eclipse records is not a historical curiosity or an academic footnote. It is a practical operational reality. The JPL Planetary Ephemeris, the master reference document for the positions of all bodies in the solar system used by every active spacecraft navigation team, incorporates historical astronomical observations, including the Babylonian Saros series eclipse records, to anchor long-range calculations against verified historical events. When engineers are calculating where to point an antenna to reach a probe currently beyond the orbit of Neptune, the Babylonian observational record is part of the mathematical infrastructure supporting that calculation. The Oriental Institute at the University of Chicago has been translating and analyzing cuneiform texts for over a century. Its published translations of Sumerian and Babylonian astronomical, mathematical, and literary tablets are the standard academic references in the field. The scholars there approach these materials as primary source documents from a sophisticated intellectual tradition that made genuine and lasting contributions to the history of science. Their work makes clear that the Sumerian astronomical record is not a collection of myths with astronomical names attached, but a body of systematic observation and mathematical analysis that deserves the same serious scholarly treatment as any other major scientific tradition. What all of these researchers have in common is that they engage with the ancient astronomical record on its own terms, asking what it actually says and how accurately it describes the sky, rather than filtering it through assumptions about what ancient people could or could not have understood. When that question is asked with appropriate rigor, the answer is consistently more impressive than the popular image of ancient astronomy would suggest. The specific calculation this documentary has been examining, the precessional framework pointing to a mid-21st century transition, sits within a body of astronomical work that has been found to be accurate wherever modern methods have been able to check it. The people who made that calculation knew what they were doing. The number they produced has survived intact, and sitting inside that number, pressed into the clay of ancient tablets, and preserved across 5,000 years of human history, is a message about how to approach the period we are about to enter. The oldest city on Earth does not appear in most lists of famous ancient places. It does not have the visual drama of the Egyptian pyramids, or the cultural familiarity of ancient Athens, or the biblical associations of Jerusalem. It sits in the flat southern desert of Iraq, near the modern town of Abu Shahrain, in the Diyarbakir province. And from the outside, it looks like a series of low mounds rising slightly above the surrounding land. Those mounds are all that remains above ground of Eridu. Archaeological teams working at the site, initially under the Iraqi Directorate General of Antiquities, and later in collaboration with international researchers, have dated the first permanent settlement at Eridu to approximately 5400 BCE. That makes it one of the earliest known urban settlements in the entire archaeological record. Eridu is where the Sumerian story begins in the most literal possible sense. The city that came before the cities. The first attempt by human beings to build something permanent and organized on a scale beyond the individual family or clan. The Iraq Museum in Baghdad holds Eridu period material among its collections. The museum has had a painful recent history. During the conflict of 2003, it was looted and thousands of objects were removed or damaged. International recovery efforts in the years since have returned a significant portion of what was taken, and the museum has reopened and continues to operate as the primary repository for Iraq's extraordinary archaeological heritage. The Eridu material in its collection represents some of the earliest written records of organized human thought that survives anywhere. Among those early records are what modern scholars working with the texts have identified as guidance documents. Not religious instruction in the devotional sense, but recorded observations, drawn from the long institutional memory of the Sumerian scribal tradition, about what practices and social structures had proved effective during periods of major transition in previous cycles. Harriet Crawford, whose book Sumer and the Sumerians, published in its second edition by Cambridge University Press in 2004, is one of the standard academic references on early Sumerian culture, describes how the earliest Sumerian cities developed systems of cooperative resource management that were explicitly integrated with their astronomical observation practices. The agricultural calendar was organized around sky observations. The timing of planting, of irrigation management, of harvest and storage decisions was all coordinated through the astronomical record that the scribal institutions maintained. The distribution of resources across the community was regulated through institutional structures that were embedded in the temple complex, which served simultaneously as religious center, administrative hub, granary, and astronomical observatory. This integration of sky watching and social organization was not incidental. It was structural. The Sumerian understanding of their place in the large astronomical cycle meant that the institutions maintaining the observational record were also the institutions maintaining the social fabric of the community. Disrupting one disrupted the other. Maintaining one supported the other. What the early texts from Eridu and the broader Sumerian record suggest, when read in the context of the full processional framework, is that communities which maintained their cooperative resource systems and their astronomical observational practices during transition periods were the ones that preserved their institutional knowledge through those transitions. The communities that abandoned those practices under the pressure of disruption were the ones that lost the most and required the longest time to rebuild. This is not described as moral instruction. It is not presented as divine commandment. It is presented as observed historical pattern across what the Sumerians understood to be multiple previous cycles. We maintained these practices and these outcomes followed. We did not maintain them, and those outcomes followed. The Sumerian intellectual tradition was empirical at its core. It built its guidance from accumulated observation, rather than from authority or revelation. The practical content of what they identified as effective during transitions is consistent across the texts, and it comes down to a few clear themes. Communities that found ways to share resources across existing boundaries, rather than retreating into smaller and smaller units of mutual protection. Communities that kept their observational and record-keeping practices functioning even when other activities were disrupted, because those practices were what allowed the community to orient itself and make effective decisions under conditions of uncertainty. Communities that understood a transition as a passage through a difficult period rather than as a permanent ending, and therefore continued to invest in things that would matter on the other side of the transition, rather than consuming everything to survive the present moment. The people who left these observations in clay at Eridu could not have imagined who would read them 5,000 years later. They did not know what language those readers would speak, what technology they would have, what world they would be living in. They pressed the observations into clay and trusted the medium to last. It did. Everything in this documentary up to this point has been about the past, about people who lived thousands of years ago, things they observed and calculated, knowledge they preserved and passed forward. The evidence has been laid out carefully. The astronomical mechanism is real and measurable. The mathematical capability of the people who did the calculation is verified through multiple independent lines of evidence. The survival of the knowledge across 5,000 years of history is documented. The convergence between the ancient calculation and independent modern scientific findings is a matter of record. This part is about now. The majority of people watching this documentary will be alive in 2060. That is not a projection or an estimate. It is a straightforward demographic fact. Global average life expectancy in 2024 sits at approximately 73 years, according to World Health Organization data. A person who is 40 years old today has strong statistical odds of living another 3 to 4 decades. A person who is 30 today is almost certainly going to be alive in 2060. A person who is 20 today has every reason to expect to see 2080. A child born this year will be in their mid-30s when the central point of the Sumerian transition window arrives. The year the Sumerians calculated is not a distant future that will affect other people. It is within the living memory of the majority of the human population as it currently exists. The transition window they identified as the boundary between one 2,160-year age and the next is not something that is coming. In the terms of their own framework, using the opening edge of the transition window, rather than its central point, it is already here. That changes what this information is. A calculation pointing to something 500 years away is historical curiosity. A calculation pointing to something within the next few decades is a different kind of thing entirely. The Sumerian observational record and the independent modern scientific research that converges on the same window suggests two things simultaneously. The first is that this is a period of unusual pressure. Multiple large systems, environmental, technological, social, political, are approaching conditions of significant change at the same time. That convergence of pressures creates disruption, instability, and the kind of uncertainty that most human beings find deeply uncomfortable to live inside. The second thing is that this is a period of unusual leverage. Systems under pressure are systems in motion. Systems in motion can be influenced by forces that would have no effect on the same systems when they are stable. The Sumerian observation that communities which maintained cooperative practices and continued investing in their long-term capabilities fared better through transitions than communities that abandoned those practices is not a mystical claim. It is a systems observation. During periods of systemic instability, what you choose to maintain and what you choose to let go of carries more weight than it does during stable periods. The decisions being made right now, individually and collectively, about what to invest in, what to build, what to preserve, and what to reorganize, are decisions that carry unusual weight, precisely because they are being made during a transition window. The Sumerian framework does not specify what those decisions should be. It records that the decisions made during transitions shape the character of the age that follows them. A new 2,160-year cycle does not begin in a neutral condition. It begins shaped by what the transition period produced. This is the weight of the calculation. This is what those 2 clay tablets in room 55 of the British Museum are actually carrying. A message from people who had watched the sky long enough to see the large cycle, who had seen enough transitions to know their character, who calculated when the next one would come, and built that calculation into the most durable medium available to them. They could not reach forward across 5,000 years and speak directly to the people who would be living inside the transition they calculated. They could only leave the calculation behind and trust that whoever found it would be able to read it. We found it. Come back to room 55. The Mullapin tablets are still there. They have not moved. They sit in their glass case on Great Russell Street in London, exactly as they have for decades. exactly as they sat in Ashurbanipal's library in Nineveh, for centuries before the archaeologists found them. Exactly as they sat before that, in the scribal archives of Nippur, where the hands that pressed them into clay worked by lamplight in a city that no longer exists. They are small. That remains the first thing anyone notices when they actually stop and look at them, rather than walking past, small and quiet, and in no way dramatic to look at. In a museum full of objects competing for attention, they do not compete. A piece of royal gold jewelry in a case nearby will pull every eye in the room before these two tablets attract a second glance. But look at them now with everything covered in this documentary present in the mind. Look at those wedge-shaped marks pressed into the clay surface, and understand what they actually represent. These tablets are the physical record of a calculation that was produced by people who understood something about time that most of their contemporaries did not. They understood that time moves in cycles, large cycles that completely dwarf any individual human lifetime, cycles that the records of many lifetimes, stacked carefully together and examined with mathematical discipline, can detect and measure and project forward. They built that understanding through generations of careful observation, through the maintenance of a continuous institutional record that survived political changes and conquests and cultural disruptions across centuries. And at some point, they looked at what all those records were telling them, and they calculated where the large cycle was going. The number they arrived at pointed to a time they would never live to see, a transition in the slow turning of the sky that would not come until thousands of years after everyone working on the calculation was gone. They could not send a messenger forward in time to deliver that number. They could not write it on a medium that would survive reliably across millennia. Papyrus rots, wood burns, stone can be quarried and reused. But clay, pressed with a stylus and left to dry and harden, turns out to be among the most permanent things a human hand can produce. They chose their medium well. The specific calculation they preserved says that the spring equinox sunrise is currently crossing from the constellation Pisces into the constellation Aquarius, in the framework they built around the great precessional cycle. The central point of that crossing falls between 2060 and 2080, by the calculations derived from their own numbers and their own framework. The opening edge of the transition window, by multiple scholarly calculations, is in the early decades of the 21st century. The majority of people alive on Earth right now will see that central point. Many of them are living through the opening of the transition window right now. The Sumerians who calculated this were not prophets in the religious sense, and they were not mystics. They were scientists working at the limits of what their tools and their era allowed, and within those limits, they were extraordinarily precise. The Venus synodic period they recorded differs from the modern measurement by less than 0.1%. The precessional rate they calculated differs from the modern measurement by less than 0.5% across a 25,000-year cycle. Their eclipse prediction cycle, the Saros, was accurate enough that a modern space agency uses it as calibration data. The calculation pointing to a mid-21st century transition sits within the same body of work. It was made with the same methods. It deserves the same level of seriousness. Their message was straightforward. We were here. We watched the sky long enough to see the large cycle. We measured it as carefully as we could. We calculated where it was going. We are passing that calculation forward to whoever comes next, because whoever comes next will be living inside the transition we calculated. And we want them to know that it is not an ending. It is the boundary between one age and the next. The cycle continues on the other side. What the next age looks like depends on what happens during the transition. Take care of what matters. Keep watching. Keep the records. Pass them forward. Step outside on a clear night and look up. The same sky is still turning overhead. The precession is still happening. The equinox sunrise still moving slowly across the zodiac, at the same rate the Sumerian astronomers measured, by watching night after night across generations, until the pattern became visible. The tablets in the British Museum are the record of that watching. They survived everything the world threw at them for 5,000 years to reach this moment. The question is, what we do with what they left behind.